So, I guess we'll go ahead and get started. Thank you guys for coming. This is my first time really giving a talk that's this length on any of the research I've been doing. So I really appreciate the opportunity to do a first run here with people from the bar. So I'm Jake Arkin. I'm a PhD student here, second year. I'm in the electrical and computer engineering department. I'm working with my advisor, Dr. Thomas Howard. The majority of my research has been focused on learning models for human-robot collaboration through natural language understanding, but the lab itself looks at a much wider breadth of research, which I'll talk about more at the end. I'll give a little background about who I am and the education that I've gone through. So I've actually been here at the University of Rochester for 7.5 years. I started as an undergrad in ECE back in 2009. I graduated in 2013 and decided to stick around for my master's in electrical and computer engineering. Did that in a year, graduated in 2014. I focused on wireless communication theory and machine vision, so I took digital video processing and the machine vision course here. And it was essentially as close as I could get to robotics without also doing the mechanical engineering side of things. So when I first joined, I joined as a PhD student in January of 2015. It so happened to be the same time that Dr. Howard was joining as new faculty, which worked out really well for me. It was an opportunity to do research in a field that otherwise really hadn't been explored here at the university for some time. And it was an opportunity to work with new faculty, which is unique and exciting and very aggressive in terms of the amount of work that you try to get done. When we first joined, the lab that we're in now, which is Gavit 146, was under renovation. So it was a pretty interesting first few months. We obviously couldn't work in that area while they were doing construction. So we were put in Hilton 331, which it's a little hard to see because of the lighting, but it's essentially a small storage room. You can see here, those are a bunch of desktop backgrounds. So that was where I was actually doing some work. I shared this space with Baxter, our first robot that we got, who's an immobile two-arm manipulator robot. And this is essentially the environment I was working in for the first 3 or 4 months, essentially from January through the end of April. So since then, the lab has come a long way. You might see some of these faces behind you. The lab has grown to have 3 PhD students. We have 3 master's students and 2 undergrads. And you can see our robotic platforms have expanded from Baxter to include 2 Husky robots, one with an arm, one without, and Turtlebots, which are the 2 robots on the far sides. We have 15 of those that are used in the Autonomous Mobile Robots course that Dr. Howard teaches in the spring. And I'll talk more about the research and other aspects of the lab at the end of my talk. So I'll first just describe the meat of the talk's outline. The idea is to first motivate the problem of why we're interested in natural language understanding for robots, try to formalize the problem, as well as give some related work background and some background material that's really fundamental to the research that I've done, as well as talk about 3 models that I've contributed to focusing on understanding spatial relationships in complex environments, verifying natural language symbol grounding, and natural language understanding for a space of corrections, which is an application for rehabilitative robotics. I'll then conclude with some current investigations and future directions. I'll try to spend a little bit of time on that, so if I'm running out of time, we may jump to the current investigations just so that I can kind of give you guys a sense of what I'm actually interested in going forward. So why are we interested in natural language for robots? There are a few different reasons, and I actually think this is a pretty important slide, so I may talk at it for a little while. But the first of which is just that natural language as a communication modality is very accessible to most people. And as we kind of project into the future how we think robots will be utilized in society, we're kind of anticipating autonomous cars, and we're anticipating household robots that help around in the house. And all of these require the general person to have some way of interacting with the robot, and we would like that to be intuitive so there's no formal training process you have to go through. Natural language is nice for this because, taken to the limit, these interfaces should be as efficient and as intuitive as communicating with other humans. Additionally, natural language is a multi-resolution interface. What do I mean by this? Essentially, I mean that the information that you convey in a single sentence is highly variable. And I'd like to give 2 different examples that are on the opposite ends of the extreme in this case. So for example, you could say something as low level as with the Baxter robot, you could say, move your elbow 0.2 radian, something like that, where you're using language to express a very low level hardware instruction. On the opposite end of the spectrum, you could say, robot, please go make me dinner, where now that instruction has contained within it a variety of implied task sequences. There's a lot of information that's required in order to achieve this in an optimal way. For example, it's important to know what is the user interested in having for dinner. How do you get to the location where you would have to prepare the dinner? All these sorts of things. That's really what I mean by a multi-resolution interface. Then one of the most important parts, yeah.
So you mentioned optimality. How important is optimality for this?
It's not necessarily important to find the best solution, but often we care about just having some solution that satisfies the express goal. So functionally operable in the real world is a good first target. In terms of platform agnostic, what I mean by that, the idea here is if you're customizing a joystick or some sort of graphical interface on a tablet with which to interact with the robot, that interface is going to be specialized in some way to the robot platform itself. Whereas with natural language, what we're doing is essentially representing the instruction that you've expressed in some high-level representation that can be passed on to dedicated planners and things that are customized for these robots. So in this way, the natural language interface is much more generalizable in terms of which platform you can apply it to, which is a desirable thing given how many different types of robots there are and how interesting it is to explore the different hardware modalities. Yes.
Then, how does the gamut of capabilities of a robot fit in with the idea of the language platform agnostic? I mean, there are certain things that certain robots can't do.
Sure.
And therefore, how would that language be interpreted by a robot that can't do it?
Yeah, so I think that's application specific in terms of what has your system been designed to do in failure cases. So I actually talk a lot more about that later on in the talk. There's some research that we did using logic formalisms to provide feedback and things like that, given that you might say something, but your robot either can't do it or the environment is such that it's impossible. So that's a good point, and I do talk about that later.
So what do you think the robot should do on the left if you tell it to come over here?
Say it again, the robot on the left?
Yeah.
Well, that's an immobile robot. I suppose you could exploit some notion of transparency where the robot has indicator lights and things. It could flash. It has a screen that can have text pop up on it. It could say, I cannot do this, things like that. Some sort of indication that provides feedback to the human. But there's certainly a variety of different solutions you could develop.
Philosophically, should it try to do the thing which is closest to what you think the robot could do, or do you think it should just fail and just say no?
I think that's up for debate and depends a little bit on the scenario. So different types of applications have different degrees of consequences, so extremeness in the consequence. For example, if it's a surgical robot and it's operating on some individual who's sedated, I think we wanted to go toward more cautious choices. Opposite that, you might imagine you don't have a lot of opportunities. Maybe it's a deployed robot in the field and you very rarely are humans coming to interact with it. It's more of an autonomous system in that the human in the loop is far less frequent. I think in that case, you wouldn't want it to just get stuck and stay, but you want some sort of behavior tree representation of something that tries to find different solutions. Something like that.
To your question, is decline considered a failure? I wouldn't think so.
Potentially. I mean, I think you'll get into this notion about planning versus action and other things, but the closest action to come here for that robot would be to move your hand here so the center mass gets closer to the person.
Yeah.
It doesn't actually do anything. It's not actually helpful.
Right.
The flip side of that, if you have a robot inside of a box and you just ask it to do something, and it does all these terrible things, but in the end, it eventually does the right thing, technically you don't care as long as it didn't do any harm. So I think that speaks to your example for the surgical robot side.
Yeah, the do no harm thing I think is pretty key. I guess the final point on this slide, which I kind of talk about more, is the reason I bring it up, is the notion of providing a hands-free interface or a hands-free communication modality. As mentioned, some of the future uses of these robots that we kind of anticipate are in collaborative settings between humans and robots. So one specific example that I talked about in a little bit is this cooperative assembly idea. So you can imagine a scenario where there's, let's say, an IKEA table, which may or may not be exactly what it comes up later. and the robot and the human are trying to construct it together in a cooperative manner. In that particular case, the human wants their hands free in order to perform some actions in the task. So if they have to teleoperate the robot or they have to interact with some computer in order to specify goals and things, that's not exactly desirable. We would rather have a more flexible and an efficient way of communicating that doesn't cause you to just stop what you're doing and go to the communication modality. And I know that a lot of you in the audience are pretty familiar with natural language understanding, given how popular it is as a research topic here. So I thought I would just use this slide to kind of make a small distinction between, or at least how I kind of think about the difference between general natural language understanding and with natural language understanding for robots. And it essentially comes down to how important is it that you consider the environment when trying to understand the meaning of a sentence. There are disciplines in natural language understanding that may or may not be, it may consider the environment, but there are certainly things that are just looking at the linguistic components of these things. For robots, the environment is fundamental in pretty much all cases for two different reasons, maybe more. The first of which is that the meaning of a given sentence depends on the environment. And the example I like to use is if you imagine there's a table of blocks in front of you and you have the instruction, pick up the closest block. If you then scrambled up the table and moved the blocks around, the solution or the referred to object in that case then changes according to the layout of the blocks on the table. So in that case, the meaning of what you actually are saying is dependent on the environment context. There's also real world consequences because these robots are agents that are manipulating the environment. So if there's an inaccurate understanding, so it infers something that's not what you meant, then there can be an undesired consequence where it goes and does something that could be dangerous. So for both of those reasons, it's very important to always be considering the environment when trying to understand natural language for robots. So at this point, yeah.
Sorry, about your previous slide, I feel like the environment is important for every single domain, right? Like for a conversation, you have the contextual history of how the conversation folded out, and that is your environment, right? And so for robotics, it happens to be grounded, like, real physical world.
That's true.
Yeah, so I feel like maybe it's hard to say that that's the fundamental difference from robotics domain to
I guess if you
our
expand,
kind of grounding.
Yeah, so if you include like your conversation history as part of your environment context.
Or just any capability, any action that your conversational assistant can or cannot, execute, right? So like, asking to add something to your calendar is an action, sure. Or like,
yeah, so I guess
come here is not an action.
Maybe the physical environment is a more appropriate specification.
Mm-hmm. Yeah, just to tag on. So I mean, your example with closest, that's an instance of a deictic marker, and so that can be, that relies on the environment to be interpreted, and that's the same for pronouns like I and you.
Yep.
I mean, that's just an intrinsic part of language.
Yeah, so I was using that as an example for why the environment is important.
Exactly.
Yeah,
I'm saying that's intrinsic to language itself before you even start modeling.
Yeah.
Sure, I guess. Okay, so, but would you agree that there are cases in natural language understanding where you're just focusing on linguistic features and all you're trying to do is perhaps map a language to another language? Is there necessarily environment consideration in that sense?
Just because deixis is a fundamental property of language, you won't escape it if you're working with language. Okay. That's my point. I think that there is a distinction. You're right to make a distinction with the problem, but just on the careful wording of it.
Okay, sure.
That's my own point.
Yeah, this slide is not fundamental to the majority of my talk, so it was kind of just I was trying to.
It's a very important and interesting topic, though. Like, in our community, there are people who work on natural language from different perspectives, and there's this problem that people make it specific to their domains. And what if we could have one, generic AI that just does NLU, and you can, so back to, Scott's point, the clause really has a generic inherent meaning, right? And why should we build different systems that have their own, then you can make that more task specific. So this is actually a very good topic to discuss.
Yeah, I guess I'll need to revisit the nuance.
So closeness can mean different things in terms of, closest in time versus closest in space versus closest in all sorts of other things. So, but I do think that there is a distinction in terms of this uncertain perception-based continuous representation of where things are in the world. And that's different than having a kind of semantic graph of what the world looks like. So I think, I don't know, I still would argue there still is something actually a little bit different about the way that
maybe the representation is
think about
different.
Yes.
Maybe the representation is different, but the idea that the context is the same, yeah, context in the language is like you can represent the word as like, okay, this box is next to that box, and then you're transforming that like physical like word to language word, and then everything is the same again, kind of. But yeah, definitely. But there is a transformation from this visual model of the word to the language part. But I guess from there, everything can be the same. I don't know.
Well, sometimes it's not even that we actually know that an object even exists, right? I mean, we have a distribution over whether or not there's a soda can on the table, and we get that from all the uncertainty we have from our cameras and all of our rated fighters and everything else.
Yeah.
I think mostly outside of robotics, there's an assumed world model that you kind of know.
Yeah.
So here it's another level. Basically, it's another level of uncertainty.
So I like that. Like I think that's the uncertainty of your recognition is something that we don't deal with.
I mean, actually, it's
much in the context of say a conversation.
but I don't want
like
Yeah.
Yeah, this is clearly a really interesting problem, right? And I think it's actually not that unrelated to like what is a robot. People argue that virtual agents sometimes are robots. Field roboticists may argue against that. So I don't know that this is necessarily a solved question, and it's certainly really interesting. So maybe we can talk about it later. All right, so this is my formal representation of the problem description. So the idea here is we're trying to find the most likely robot motion or robot behavior given some language input and some representation of the environment. And so I like presenting this because I think it's a really nice way of kind of introducing the problem for robots. And it's also interesting because it's a nice simplified way of thinking about the problem. But this is a really hard problem to solve, and it's mostly because of the space of these variables. So for example, the robot motion, if your motion is representative of some high degree of freedom platform, like a 6 degree of freedom arm manipulator, and you tell it to go to like pick up a mug, you're sampling trajectories in this continuous action space, and there's an arguably infinite number of trajectories that all achieve that solution. So the space of robot motion can be very large depending on the platform that you're actually interested in. The environment representation can be complex or simple, and determining which of those it is can be a challenging problem in itself and also conditioned on language. And the example that I really like to give for that is you can imagine you have some robot manipulator, an empty table, and a single coffee mug. If you just say pick up the mug, the minimal representation for the environment may be something like a simple bounding box representation for the table in order to avoid any collisions, and some simplified object representation for the mug that's sufficient for the robot to pick it up in some way. But if you then said pick up the mug by the handle, you now need to decompose your representation of the object, the mug, to now incorporate some notion of handle, as well as sufficient resolution of that in order to identify viable grasp points to pick it up. So the environment representation is also difficult to model, and it's not always obvious what the best representation for that is. And additionally, language is also just very difficult in general to model. The opportunities for different inputs that mean the same thing or map to the same thing from the robot's perspective is very high. In addition, there can be language that's very similar but actually mean very different things. So all of these things make it a very hard problem to model, and that's why I think it's so interesting and exciting to research. So I'll use this as an opportunity to transition to some related work in the field. So this is a small sampling of related topics. Some of them have a different twist that I think is interesting. So starting at the top left, this was work done at Cornell by a researcher, Dr. Adrian Botnu. It was focusing on task component substitution. So the idea is the robot has some representation of a task. Perhaps it's a hierarchical task network, and there are components of the task that are basically subtasks or actions that are conditioned on objects that the robot expects. But you can imagine there's a scenario, for example, let's say it's trying to make a salad, but there's no salad fixings, but there is an egg on the table. The robot might want to substitute the egg for the objects that it normally uses. So it can ask a question, can I substitute an egg? And then the user can provide either a yes or no feedback response, and that allows the robot to learn something about the task and how it can substitute different objects in that actual task itself. So that's just one example. There's another one that I saw this past summer. I guess it was in the spring now at the Midwest Robotics Workshop. I think it's going to be in the AAAI in this coming publication. So it's work with Raymond Mooney's group. The idea here is learning object references and properties from language. So this is actually a game scenario where they're playing the classic I Spy game. So the human would say, I spy something maybe cylindrical, shiny, and hollow. And then through iterations of these examples, the robot is able to learn properties of the objects in the environment. And some of the results that they were reporting were pretty interesting in that the robot was actually outplaying the humans in these games, and it was able to better map the properties to the specific objects. That's pretty interesting. The top right, there's a coordinated assembly task that was actually work done by both Stephanie Telix at Brown and Ross Nepper at Cornell. You may have attended Ross's talk maybe a month and a half ago now, but the idea here is this coordinated assembly task that I mentioned earlier, where you have two U-bots, which are those robots in the image. You have an IKEA table where this is the base of the table, and then there are 4 legs that have to be screwed in. U-bots have a special arm that can twist the table itself. But the idea is that there's sometimes, there are scenarios set up where the robots cannot get the objects that they need without human assistance. A help response and try to specify exactly what they need the human to help them with. So it's a slightly different take where you've inverted the problem to a language generation problem, but it's still important because, or it's still relevant because you have to understand what you're expressing. In the bottom left, this was work done in 2011 on looking at the turn-taking aspect of dialogue and how that impacts the fluency of different interactions. So they were trying to optimize when the robot would actually interrupt and provide some information. So I thought that was interesting because I'm starting to look at more of this kind of dialogic interaction as opposed to just one-directional understanding. And then on the bottom right is actually some work that I saw this past summer at RSS, which is Robotics Science and Systems. This is work from TTI Chicago. They are looking at, let's say a robot has come from somewhere and arrived at your location, and you say, well, where have you been? So the idea here is to be able to use its history of where it's been and generate some natural language instruction that expresses what the behavior it's been doing. So it's another language generation problem, and I think it's interesting to just think about that direction. There's some more related work that's that I talk about here. I choose to spend a little more detail on these because they're more directly related to the work that we're doing. So these are generalized grounding graphs, which is some work done by Stephanie Telix at Brown. So the idea here is to represent the natural language understanding problem for robots as a probabilistic graphical model, where the structure of the graph itself is conditioned on the constituency parse tree representation of the utterance, which is shown on the left. So in this particular example, we have move near the green block, or the green box in the blue crate. And this is the graph representation where there is a conditional independence assumption on the individual phrases in the constituency parse, the exception being that parent phrases are conditioned on the expressed symbols of their child phrases. So that would be what these connections are here. This line is connecting to and to indicate the connection between the noun phrase, the green box, and the noun phrase, the blue crate. The idea behind each of these individual factors is we're assuming, or we're trying to find the robot action or the physical concept that would be grounded to the sentence. We're trying to find an association between that and the blue crate. Let me say that again. Each factor is trying to find the most likely grounding given some true association between that grounding and the expressed language. So the search itself is trying to find the most likely grounding, and we're assuming the correspondence is known and that the language is also known. Implicit in the graph is the upsilon, which is our environment model. It doesn't change at any point, so we keep it off of the graph in order to make the graph representation a little cleaner. So how exactly does this work? The idea is that you can have a variety of robot behaviors, which are your possible groundings for the language. And you have some utterance, let's say go to the blue box in the green crate, and you can sample from the space of possible trajectories and learn which ones are most associated with that by asking people to decide. So in this particular case, X1 is actually the motion that most matches the sentence. And you can see X3 and X4 are pretty much completely wrong. But X2 is interesting because it's pretty close, but not quite as representative as you might say X1 is, for example. So the idea is you have human users give you a distribution of solutions or behaviors that map to this language, and you're able to learn the likelihood of which behavior is mapping to the individual phrase itself. So there are some issues with this, or limitations to this model. One of which is just as the complexity of your robot platform increases, that space of robot behaviors becomes massive. So, for example, in this particular case, you just have some robot moving around in two-dimensional space, has an orientation and a position, has control over its angular and linear velocities. But if instead you just put a Baxter on top of it, now you also have two 7-degree of freedom arms that you have to consider, and your space of possible behaviors has exploded. So this is a problem because it makes real-time search intractable as the complexity of your environment increases and your robot platform increases. So this was something that Dr. Howard actually recognized as an issue, and during his time at MIT in 2014, he had the idea of, instead of trying to find the most likely robot behavior, we can represent sets of equally representative behaviors as motion planning constraints. So in this particular case, we have admissible, inadmissible, and goal regions, where the black space is your admissible region. That's the area in which the robot's allowed to operate and move around. The white spaces are inadmissible, and they're there to prevent any kind of collision. And then the gray in around the blue is the goal region. So that's where the robot wants to end up. And interestingly, you can also consider each of these individual constraints independently and just express the union of them in the final. So what this leads to is actually the majority of the background material I want to cover, which is this distributed correspondence graph, which is work that Dr. Howard did in 2014. So the idea here is we've changed the factor representation where we are expressing the groundings as possible robot behaviors, which are trajectories in the state action space. And the factor expression itself assumes a known language and known correspondence, and you're searching for the behavior. We now change that to assume independence across the possible expressed constraints. And we assume that the space of constraints is known because it's finite. And we're searching for the most likely set of correspondence variables to represent the association between the language and the motion planning constraints, or a set of motion planning constraints. So,
sorry, what is the range of X and U?
yeah, U is your control input space, and then X is the behavior of robot motion.
What is it like? Is it velocity and or just go to a point kind of?
It depends on the representation you want to use. But, yeah.
So what would it be for the mobile robot? Your
Linear and angular velocities.
what would your execute?
It would be a time sequence of points in space that represent different positions and orientations at close time sequences.
Pass.
Okay.
Yeah. Do you accommodate things like if the robot is a great distance away from the target as opposed to being closer, do you change the goal space? I mean, what does near mean when
Yeah, that's a great
10
question.
meters away against 10 centimeters away?
Yeah, that actually goes back a little bit. I probably didn't cover this well enough. But you could imagine you could have this like a set of X1 where they're all similar but slowly getting further and further away. And then you ask a variety of humans whether, like, at what point don't you consider it near anymore? So you get a distribution of solutions or distribution of answers according to your human sample. So that's kind of how we address those subjective terms like near and far, and leftness and closeness, things like that. So here's the actual distributed correspondence graph formulation at the top. The idea here is we're trying to find the most likely correspondence variable given some individual language phrase, a space of groundings that map to that, or that, yeah, sorry, let me say it again. we are trying to find the most likely correspondence variable given some lambda sub I, which is your language phrase, some gamma sub ij, which is the jth grounding constituent of your lambda phrase. So in this case, it would be motion planning constraints. Some set of child correspondences, which is your phi sub ci, and some set of child groundings, which is your gamma sub ci, and then the environment representation, which is implicit. So this is not always easy to just immediately understand. So I tried to decompose the construction of this graph in a way that is kind of how I think about it. And we'll go from the assumptions that we make and try to build our way up to this actual model representation.
Clarification.
Sure.
So you mentioned all of your gammas are your motion planning constraints.
Yeah.
Only your motion planning constraints?
No, that's just one example. But you can imagine if you're grounding to the phrase, the blue block, there's not necessarily a motion planning constraint associated with that. It's some object representation that has properties of color and properties of type. So the high-level actions are represented as constraints, but we can still assume conditional independence across the expression of those boundaries, which is really the key point there. All right, so if we start and try to represent a graphical model all the way back to kind of the same problem description that we had originally, we start with this idea of trying to maximize the set of correspondences given your environment, your language, and your space of possible groundings. If we assume conditional independence of the linguistic constituents, which are your language phrases and your constituency parse, then you can factorize the model it's shown in the second equation, where we're now searching over the phrases I through the set n. And if you then assume further conditional independence of the individual constituents themselves, you can do another product of factors over those groundings. So in the graph construction, this equation expresses the different factors horizontally, and the conditional independence of the grounding constituents is what expresses the vertical factors in the graph. And I think that'll be more clear over the next few slides. So we'll start with this really simple example, move near the green box. This is the full DCG representation with some ellipses notation in there. So the way this would work is you would start at the right. So this is a directed graph starting in the bottom right. The full vertical set of factors are the space of possible grounding constituents for the first language phrase. So the search in your graph tries to resolve or evaluate the likelihood of each of these correspondence variables for all of your constituents. So once you've done that for all of them, those that are most likely to be expressed as true get incorporated in the next factor evaluation for the next language phrase. And yeah, so the search of the graph essentially starts in the bottom right, goes up. Different groundings get expressed according to likely correspondences, and then you repeat the process for the next phrase.
So sorry,
Yes.
what was lambda again?
Lambda is your language. Yeah, it's in one slide. Sure, lambda is your language. So in this particular case, lambda 1 would be the phrase, the green box.
And what is the representation here? Go down to features, green box as counting.
Sure. Yeah. So the gamma sub 1, 1 would be your first grounding constituent that you would consider for the phrase, the green box. And then you would go all the way up through the j total number of constituents. You would try to evaluate the likelihood of the correspondence between the single language phrase and each of those grounding constituents. And so you do that all the way up. And the nice thing about this is that information at the bottom of the tree propagates up until you have some high-level representation that hopefully has captured all the information expressed at all points in the tree. So I'm actually going to talk more about the factors here and just describe specifically what the variables are. So the top left is the evaluated expression we're interested in. This is a single factor. The gray is there to indicate that those nodes are essentially implicit in the graphical model that I showed before. The whites are assumed to be known, and the green circle is what we are searching for. So the lambda sub I is the ith phrase of the utterance. Would be like the green box, for example. The gamma sub ij is the jth grounding constituent of the ith phrase. The correspondence variable phi sub ij is the correspondence between the ith phrase and the jth grounding constituent of the ith phrase. And capital gamma sub c sub I is the set of expressed groundings for the child phrases. And it is kind of shown in the graph, but I have it gray here because we don't explicitly represent it using this variable. And then epsilon is your environment model, which is implicit and doesn't change throughout the expression.
So I don't completely understand what a correspondence amounts to.
Sure. In this particular representation, it's a ternary expression, so it can either be active, inactive, or inverted. That's just referring to the motion plane constraint part of things, where motion plane constraints represent disjoint regions of space. So the idea there is, let's say you didn't want to collide with an object, you would have some constraint about how close you can get. So that would be some inside constraint, but there's a boundary. And if you wanted to express the opposite of that, you could invert that constraint. And then if you don't care at all, then you would just have it as an inactive constraint. But most of the time, it's just binary. So it's either true or
For
false.
the example of the green box or the.
Yeah, so most of those would either be true or false. So for example, let me go back to this. Let's say that this grounding constituent here is a blue box, and this grounding constituent is a green box. The idea is that it would learn some weights on your features in your factor representation that informs you that it's unlikely to be the blue box, so this would be false. And it's likely to be the green box, so that would be true.
So for near, I'm trying to imagine the constraints in the motion planner. Is it like, do you have a distance for, I don't know, how big that circle that the forbidden region is? Like, is it, or it's fixed region is like always 2 meters or something?
Yeah, I think that depends on the application itself and also just the data you've collected to train on.
For that specific 2D things, 2014
I wasn't, I didn't contribute to that work, so I don't know specifically. I think that they had a set of possible distances and they were able to learn the most likely one according to the rest of the environment context.
So I can come on it. So the planners often interpret nearness as either a constraint or a cost function, and those cost functions are often learned, but sometimes they're just chosen based on whatever the person likes for the application. Mark Campbell at Cornell is actually working on this thing that we're actually starting to use now, where you just try to learn this distribution of what needs to be near, left of, above, below, inside, whatnot. The idea is actually to marry the symbols that we're using to represent nearness or left of or right of with these distributions that you can actually use inside of your planner. So
yeah, you could also imagine having some having a cost gradient around that object where it's not as costly to be maybe a meter away, but as you get further, your cost increases, and so trying to optimize the.
There are things that are more deterministic, like contact, right? So certainly, the power strip is on the table, and on means above and in contact and all sorts of other things. Whereas above might mean not in contact.
Yeah.
Well, I guess that's actually debatable. So that's one of those inverted, not inverted. That's one of those inactive correspondence variables. We would say it doesn't actually matter whether it's in contact or not in contact. It is true that it is above. So left of, right of, although it doesn't deal with the reference issue, are things that are more like inequality around maybe the local XY or what's playing.
So Guillaume Latham is working here, working on the same issues.
Yep.
Should be some.
I talked to him on a bowling.
Oh, is that right?
Yes.
Oh, okay.
All right, so each of the factors themselves we represent as log linear models with binary features, and the idea is to learn some set of feature weights that map to those features, and we utilize the LBFGS algorithm for optimizing those feature weights. So some examples of features in the phase DCG model that you might be interested in are lexical features such as unigrams or parts of speech tags associated with individual words. There's also spatial features such as leftness and rightness, as well as object features that just identify whether an object is of a specific type or a specific color, has a specific pose relative to other objects. I'm taking a little longer than I was anticipating, and I haven't gotten to exactly what I'm doing yet, but at this point, I've covered the background material, and I'm going to talk about 3 different models that I contributed to in the past year and a half or so, each kind of tackling different problems. So the first one is trying to understand spatial relationships in complex environments. So this was work done with Dr. Rohan Paul and Dr. Nicholas Roy at MIT, the robust robotics group there. The idea is that we want to be able to understand sentences like pick up the middle block in the row of 5 blocks on the right. These types of sentences are especially important when there are insufficient visual features about the objects that you can use to specify what you're referring to. So you're required to express relationships to other objects in the environment. And sometimes when you do that, you express these things that we've coined as abstract spatial concepts, such as the row. So what does it mean to be a row? And that's really what we're interested in trying to understand. We want to do that in real time, and we want to make sure that the computation is efficient, because the base DCG framework is capable of understanding that instruction, assuming that you can express symbols for it, but it becomes a very hard problem because the space of symbols becomes essentially the power set of all objects in your environment. So for example, in this case on the right, the space of abstract symbols for the base DCG representation would be 17.3 times 10 to the 6 symbols, which makes real-time search intractable. So it's a hard problem because of how large the search space is, and our goal is to efficiently be able to understand these concepts. So our approach was to discretize our symbol space into either concrete or abstract symbols. What do we mean by concrete and abstract? Essentially, the concrete symbols are principal physical concepts in the environment that we can use to inform properties of the abstract concepts. So for example, objects or actions in the environment, or cardinality referring to objects in the environment, spatial relationships between individual objects. Abstract spatial symbols, we use that term to refer to both containers, which could be things like rows and columns, or a pile of objects in the environment, as well as different attributes related to those, and relationships associated with the concepts themselves. So for example, the middle block in the row. So how do we do this? We use a joint distribution where we introduce these concrete and abstract factors. Model evaluation is very similar to what it was before, except now we've expressed this distinction between the two symbols, and the direction of search is conditioned on both the expression of concrete and abstract symbols. So what do I mean by that? Here's a new factor model factor graph representation. The idea is that the space of abstract symbols that we are interested in looking at can be inferred through the expression of these concrete symbols. And so we can first look at the concrete symbols and utilize the expression of certain concrete symbols to inform a dynamic construction of the abstract search space. So rather than searching through all possible abstract concepts, which as mentioned before is a large space, we can use things like, for example, if you said the row of 3 blocks, the expression of 3 blocks gives us information about what properties of the container we're actually interested in. And so we would know that we're interested in containers that have a 3 of something, and we would know that we might prefer things that have blocks in them. And if we said it was the row of 3 blocks, then we know something about the type of the container that we're interested in. And so we can dynamically construct that abstract space according to the expression of those symbols.
You distinguish between A middle block and B middle block, being 3, picking up block 3 versus 2 through 4.
So that's a good question. Essentially, all of this is trained on human examples. So it's a function of whether we give examples that allow humans the opportunity to identify something like that. Almost always, I mean, we never presented a scenario like that. We always only had people picking up individual blocks, or robots picking up individual blocks. But assuming we had the examples, it seems like something we'd be able to address. So here are some example utterances that we received during our data collection process, which I'll also describe. The idea is we construct these worlds in simulation in such a way that we think that they have these concepts that we're interested in. We then identify some set of objects using blue or green bounding boxes and put those images up on a crowdsourcing application like Amazon Mechanical Turk. And we ask a distribution of people to provide multiple utterances that would express the set of objects that we have on the table, or that we've identified in the bounding box. So these are some examples. We have things like the group of 4 blocks on the right for the one on the top right. So the idea is that what we get back from Amazon Mechanical Turk is a distribution of parse tree representations for the utterances, as well as some known root phrase symbolic representation for the concept itself.
So the Turkers are seeing the simulations.
Yeah, so the video on the right is actually something, the series of videos are what we use to get a lot of the action language. So the still images were mostly just to get the concepts, but we also showed them videos and asked them what is the language you would use to produce the robot behavior. So we're getting the utterances back while already knowing the symbol ahead of time. And again, these factors are evaluated as log linear models, and that is the same as before.
Just a quick question. So are left and right, are they always from the robot's perspective?
Yeah, that's a great question. So that's actually a problem that we're looking at. So we enforced a perspective of using the robot's left and right, but you can imagine that that does not generalize well. So we're looking at different approaches to resolve that, but yeah, that's an interesting problem.
One of the things we can actually look at, because we have a big data set that has some of this data in it, is if you just try to learn what the most likely frame of reference for the person is, wherever they're standing or whatever else, you can actually use it in a distribution of the actions you want. There's certain circumstances where the frame of reference actually doesn't matter. If I tell you to pick up the block in the middle, it actually doesn't matter whether it's left or right. So that distribution would actually give you the same answer. So then you're really certain. If you're sufficiently unclear about whether it's my right or your right, that's exactly the point where you have this two-peak distribution. And then the robot should ask a question if it's actually unclear.
Yeah. So let's see. Here's some of our experimental results. So we compared the accuracy of our adaptive search to the baseline distributed correspondence graph representation. The idea here was to demonstrate statistically equivalent accuracy while showing significant increase in runtime performance. So these are the accuracy results. We used two different accuracy metrics. One is just comparing the root phrase symbolic expression of the full utterance, so both the ground truth and what was inferred, and also looking at each phrase within the entire parse tree. The second metric is less likely to be, well, we had worse results for the full complete phrase accuracy, which makes sense. What this demonstrates is that our model is capable of handling some inaccuracy somewhere in the tree that gets resolved as the information merges up the tree. So it's robust to some individual phrase inaccuracies. The bottom two graphs show both the baseline and our model. The accuracies essentially trend on top of each other and fall heavily within the error bars. So the idea here is just equivalent accuracy with significant increase in runtime performance, which was the main goal here. So we evaluated the runtime performance of both models as a function of the number of objects in the environment. Really, it's the complexity of the environment, but what we specifically did here was just look at how many objects there were. So we looked at worlds with 4, 7, 5, 7, 10, and 12 different objects. And you can see that the DCG model for the world with 12 objects was taking an average of 14 seconds to infer the meaning of some sentences, where our adaptive model was still heavily under 1 second. And the scalability of our model is, the idea here is that our model is able to scale much better with the complexity of the environment without any loss in accuracy. Here are some more examples of different utterances that we looked at and received back from Amazon Mechanical Turk with some nice color-coded visuals to just kind of identify the physical representation or the physical component associated with the different parts of the language.
So instructions is the number of instructions in that specific data set. Like you have 4 instructions for one.
That's right. Yeah. So the instructions column is referring to how many examples are in our corpus that have that many objects in the world. Yeah. And here's a video of the robot actually doing this. I think it should play. So there are 2 different instructions that get executed. Not using the live perception system, which is why there's a little piece of tape on the table. Since doing this experiment, we've incorporated live perception of the scene using XTION Pro, which gives us some point cloud representation, which we can use to segment different objects and find the table. Baxter, the robot in this video, also has cameras in his wrist. So when he's over an object, we can use information from the camera to locally servo until we're confident that we're over the object and can grasp. So we were having a lot of inconsistencies using dead reckoning, which is an open loop approach to grasping the object. And after incorporating the visual servo link, our success has gone up significantly. So the other problem space that I was interested in, I think I'll talk about this one. I'm running a little over on time, I think.
You have until 2, so I mean,
Okay.
given that we have Q&A
Sure.
incorporated, so.
Okay. Then maybe I'll talk about all 3 then. So this particular problem was essentially, are we capable of verifying the feasibility of different instructions given the environment context? So I like to think about this similar to how we change the representation of the problem from being behaviors in the state action space to instead being some sort of high-level constrained optimization representation. We could also choose to represent this in a verifiable task planning way. And one motivating image you might think about is you have a table with some tools on the table, and Baxter is able to pick them up. And you say, hand me a wrench, but there is no wrench on the table. So this ties back to your question earlier. What should the robot do in this case? And is it capable of even understanding that there isn't a wrench? So maybe it will force itself to pick up a screwdriver because that's the closest thing to wrench that it could see. So we're interested in kind of addressing this problem of what happens when some high-level expressed instruction is not feasible given the environment. So this, we looked at logical formalisms, and specifically linear temporal logic, as a way of expressing high-level instructions in a representation that we can actually do a verification on. So linear temporal logic is nice because you can express these high-level instructions using LTL specifications. So for example, you could say something like, do not enter the kitchen, visit the lounge, control various rooms in the environment, where this is your environment. And the idea is to be able to then generate some robot controller that can perform those actions while reacting to changes in the environment. So this is some work that's been done at Cornell. I guess there's a little background on LTL. So LTL is composed of propositions and operators, where propositions are either sensors or actions, where sensors are observations about the environment, and actions are behaviors that the robot can take accordingly. There are also memory propositions, which are used to remember certain deterministic responses to some sensing action or some behavior the robot has taken. The operators are either Boolean or temporal. The one example I like to use to demonstrate the temporal is, for example, if I told the robot to pick up a block and there was no block on the table, I could tell it that eventually always there will be a blue block. And so in some infinite time series, I'm essentially guaranteeing that a blue block will appear. So you can combine the propositions and operators to construct linear temporal logic formulae, which could also be expressed as structured English. And this is the representation that the symbolic representation we are interested in mapping language to. So the idea is you can go from some LTL specification and using algorithms produced at the verifiable robotics group at Cornell, you can automatically synthesize and generate a guaranteed hybrid controller that takes input from the environment using sensors and produces actions in the environment using these action specifications. And so it goes through the synthesis process, verifying that the action itself is feasible. So the idea is, can we exploit the probabilistic grounding nature of the distributed correspondence graph in conjunction with the formal synthesis process that I just described? And the answer is yes, we can. So the idea behind the VDCG, or verifiable distributed correspondence graph, is to essentially use the same framework as the distributed correspondence graph, but to modify the symbol space construction to represent the problem as these LTL formulae. So we introduced sensor and action symbols, which are just symbolic representations of the sensor and action propositions in LTL, which can be combined into these what we call scopes, which are the LTL formulae themselves. So the idea is that given some action instruction at the top level of our instruction, our root phrase representation should be some LTL formulae or set of LTL formulae. So the full process for our model construction begins with the development of the symbol space. So we know what our space of possible action symbols, space of possible sensor symbols are, and what the combination of those can produce in the LTL formula space. given those symbols, we can choose a subset of them and apply the synthesis process to generate some controller, which we then implement on a simulated Baxter robot for a variety of different environments, with the task of sorting the cubes according to color. And sometimes the cubes are there, and sometimes they're not, and sometimes the bins are covered or not. So the idea here is to have different environments with different degrees of feasibility about different subcomponents of the task itself. So once we have these reported videos where the action is paired with the high-level LTL specifications, we put them up on Amazon Mechanical Turk as we did before. We ask for a series of or some set of instructions that map to the behavior that they see. And so what we get back is a distribution of constituency parse trees as well as a known root phrase symbolic representation. So it's our job as the expert annotators to find some logical and consistent way of filling out the rest of the trees that applies to the full corpus or all of the examples we've received. Once we have the full corpus, we can use the LBFGS algorithm to find the optimal set of feature weights for our binary features, which is our training process. Once we have the trained model, we can accept novel input. And the idea is we convert the novel input, which is language, into this LTL specification. It gets passed to the synthesis algorithm, which generates a guaranteed controller, which then gets applied to the actual robot itself. So there's a video of this. Let's see. So in this particular case, the instruction was pick up the blue box and place it in the bin, pick up the red block and put it in the box on your left. See if it plays in. Okay, so the interesting thing here is essentially we've designed some state machine that has a series of goals it's trying to accomplish, but we haven't necessarily enforced an order in which they have to be accomplished. So we were a little surprised that even though the instruction was pick up the blue box and put it in the bin on your right, it actually just picked it up and then went ahead and picked up the next block before proceeding and putting the second block in the bin first. So this is interesting because it still achieves the goal, but it may not have been exactly the order in which the user wanted. So I guess this is both a good thing and a bad thing, depending on how important it is that you accurately or sufficiently specify your action.
So there could have been temporal constraints that were expressed as well, right? I mean, the instructions never said something like before or after.
Right, yeah, so you could modify, yeah, this was an underspecified instruction in that there were multiple solutions in terms of the order in which you did things that technically achieved the expressed goal. You can modify your language to say before you put something in the bin, put the left block in the bin. So it's a trade-off between choosing some goal or some solution for an underspecified instruction.
Yeah. Is it able to deal with, does it solve everything before it makes initial move? Or can it respond to changes that it has made in the environment, such as you have several red boxes and you put some in the box and then you say, pick up the closest red block and say the thing that was initially closest is now in a box that's further away.
Yeah, so I guess there's some nuance to the answer, but I think you'll be interested in some of the ongoing investigations related to providing feedback during the synthesis stage. So for example, if you said pick up the blue block, but there's no blue block on the table, during the synthesis process, it'll respond and say, this is an infeasible action. It might ask me a question and say, will a blue block appear eventually? And if I say yes, it can modify that specification to incorporate that assumption about the environment's behavior. So once you start the controller, until a blue block appears, it'll just be running and waiting and observing the environment until it sees it. The nuance is that the current implementation has blocking actions. So once it sees the block, it will go and try to pick it up. And if you then move the block away, it'll just get lost in servo and it'll eventually give up. But so I guess the idea is it's continually waiting for certain sensing properties or sensing actions to occur in the environment. For example, the bin to be uncovered. But once it observes that in our current implementation, if you revert back to something, it would fail.
Right, but if it changes something, say like there
Yeah.
are two red blocks,
Mhm.
and that, the thing which is closest to
Oh, I
it,
see. Yeah.
it actually changes that. So does the labeling that occurs at the outset stick with the blocks,
Mhm.
or is it malleable?
The inferred instruction is, it only does inference once, and then it produces some solution which includes the reference object. So if you then change things around, it'll still go after the same object that's specified, even though that doesn't necessarily fit
Because
closest anymore.
that would be different than what a human would perceive as. That, you know, if it moves things around and then finally gets, if it's executing statements sequentially,
Mhm.
and then, you know, there's a move red block prior to then do something with the closest red block, which is now a different block than it was in the beginning.
Yeah.
That the human would just go on and pick up the closest red block, I would presume.
I would say it's still underspecified, right? You know, if I just say, you know, pick up the nearest ball or something, and it's more of a, you know, just get whatever's most convenient versus get a specific object that at this time happens to be the nearest one. And if it moves away, I still mean that other object. It's kind of like the pick up this ball versus pick up any ball or pick up any something, right?
Then that depends on how you define the interpretation of your language.
That's right.
Is it a compiled or is it an interpreted language?
That's right. Yeah, so I don't even know. I mean, which
Okay,
one
I
is
mean,
correct?
Well, I mean,
Yeah.
either one would be correct, but
Right.
but it would be specified from the scratch. That's what I was asking you. In effect, are you running interpreters, or which I think would be more powerful in terms of handling complex situations?
Yeah, I can see an implementation for achieving that. I think you could just continuously be monitoring the environment and performing inference, and once your solution changes, then you update the controller. Yeah, yeah, it's definitely an interesting thing.
And that would also accommodate random craft that would happen.
Yeah, sure. I guess so. So I have maybe 10 minutes. I'm going to go through this next one a little more quickly. I think it's interesting though, because it's less of a delta on the theoretical representation of this, but more an interesting application that is useful and practical now. So this was collaboration with researchers at Northwestern, Brenna Argol, who is the principal investigator of the Argol lab there, and a PhD student, Alexander Broad. So the idea here is to allow users to provide language corrections after a robot has started to execute an action. So the reason we think this is important is because, one, we think the human should be in control of the robot. And two, we think that the user should be able to specify preferences about the robot's behavior that is easy, and we think natural language is a good way to do that. But I think the most important point here is that natural language is still available to those who have lost motor control, which would otherwise be required to interact or utilize the traditional robot interfaces like joysticks or the touchscreen interfaces, something like that. So we took a very constrained approach. We looked specifically at the space of corrections for the manipulator performing some grasp action or some just moving action. So we looked at the dimensions of corrections corresponding to the speed, orientation of the manipulator, as well as the position of the end effector itself, and the contact point on the objects that it's manipulating. So for example, you might give an initial instruction to pick up the box, but as it's going, you see that it's going to pick it up from the side, and you really want it to pick it up from the top. Maybe the box is open and the robot system doesn't have any way of perceiving that, but the human can perceive that and understands the consequences of perhaps picking it up from the side. So we can exploit the perception of the human user and their understanding of the environment and their understanding of the intended goal to update the behavior, for example, by saying from the top. So the underlying language model is the distributed correspondence graph. Here's an example parse tree where you have moved the ball over the box. The graphical representation of the distributed correspondence graph has not really changed. And all we've really done at this point is introduce some new variables in our factor evaluation which relate to the expressed correspondence and groundings of the previous instruction. So in this case, it would be those context variables would be the expressed groundings and correspondences of the pick up the box instruction. So when you say something like from the top, it's important to understand from the top, what does from the top refer to? In this case, it refers to the action that we previously specified. So we just incorporate that information in each factor evaluation. In this particular implementation, we only did that consideration for the root phrase representation, but since then we've extended this model to incorporate the context of each factor evaluation in the model. So here are some example instructions that we received back for different corrections that we tried to show. So the images themselves don't necessarily map to the language, but the idea is more just the category of correction we're interested in. So you have some interesting differences in some of the instructions where some of these exist purely as instructions on their own, and any kind of prior context is arguably unnecessary. For example, move the apple around the box instead of over it. You don't need to know that the prior was just move the apple over the box or something like that. This is in contrast to some of the examples at the bottom where you say lift from top or from the top, which are very brief sentences and or sentence fragments where the prior context is functionally necessary in order to have a fully specified action. So we actually tested this system in a human user study with 3 different human non-expert users. We built an end-to-end system, full speech-to-text, all the way through the actual robot action itself. And the point of this was both to just see how it was received, as well as look at possible points of failure going forward as we try to apply these models to other domains. So some system limitations that we recognize based on these fail and success counts is that, for one, our parser was not working very well given the instructions that the users were trying to use. One of the motivations for using natural language is that it's unrestricted and it's natural, and if you had some structured English where you have a fixed set of vocabulary that the user can use, that's not really the desired goal. The DCG model is not a parser though, so this is really just an issue with the parser that we chose to use. And since then we've applied different probabilistic parsers that gave us much better results. The other part of this is just looking at the planning runtime. So one of the features of this domain is that you'd like the correction to occur in real time. And it would be nice to not have to say stop before giving the correction. But we're limited in that the planning time after, so the language itself is inferred very quickly. It's the average runtime per inference was under 1/10 of a second. But the planning time took on the order of a second to a second and a half. So going forward for novel systems, we're interested in looking at faster controllers, which is a challenging problem. And then also we're limited by the novel vocabulary. This is trained offline in a fully supervised fashion. And if we encounter new words that we did not see in our training examples, then often we just don't infer the correct thing. So there are some limitations, and this trial was really useful in exposing those. So just as a conclusion about my contributions, I've contributed to 3 different models. I was looking at abstract spatial concepts and computationally efficient search of those. I was looking at verifiable symbol grounding, where we are talking about the verification of the feasibility of actions given the environment context and some expectation about the behavior of the environment in the future. Then I also contributed to a model looking at understanding the space of corrections to help update user preferences during action sequences. So I'll talk briefly about some current investigations. I don't have much time for that, but I think some of it is interesting. So I've talked a little bit about this first one, which is the idea that given some infeasible task during synthesis time, the robot has the opportunity to ask a question about the environment behavior, which it can use to modify the assumptions. So in this case, for example, we say pick up the red cube and place it in the left bin. And let's say there is no red cube in the environment. The robot could ask, will a red cube appear? If we say yes, then it can modify the specification to include that assumption and proceed, and just during execution, it will wait until a red block appears. Another thing we're interested in is extending that notion of context that we used in the corrections to understand monologic natural language instructions. So Currently, the distributed correspondence graph is able to infer the meaning of multiple sentences, but it essentially represents it as a single.
There is a crew too.
Okay. I'm just going to wrap up this slide then and then conclude. So the idea is that the distributed correspondence graph can infer multiple sentences, and it just represents them as a massive parse tree, where the connection of sentences is essentially expressed as an implicit node in the graph, and it's expressed perhaps as a verb phrase or something. It's not necessarily grammatically correct. So what we've done in this model is incorporate the notion of sentences. We deconstruct the utterance according to sentences as well as on a per phrase basis. And we infer the meaning of the sentences individually and in order. And we keep the context, which is the prior root expression of each of the sentences in this prior context variable representation. So what this allows us to do, and what I was trying to show in this particular example, is that you might have a sentence, pick up the blue cube, and then another sentence, drop it in the bin. In that case, you have an anaphor, which is it. The meaning of the word it is functionally dependent on the expression of the previous sentence. With the distributed correspondence graph, you wouldn't resolve the meaning of it until the very last set of factor evaluations for the absolute root phrase representation of the full set of sentences. But in this case, you would have the context of the previous sentence at the factor evaluation, which allows you to resolve the instruction immediately. In addition, we've reduced the number of factor evaluations by essentially chopping off all the factors that would be the phrase connections across the sentences. I'm essentially out of time, so I guess that is all. Thank you very much.